So one of the things I think is difficult for people to grasp whenever they're first starting to learn statics is it's kind of hard to grasp some of the figures that we draw, because we start to use sort of these symbols that mean certain things to people who are used to doing engineering problems. And I think as engineering instructors, sometimes we forget that those things become so natural to us that when people are first learning it, sometimes they haven't seen things that are in that category. And so that's what I want to start with today, is to show you a few different things that you might see as pieces of a diagram that show some physical scenario. And I want you to have a mental picture of what we might be talking about with those things, about what those really are physically. And so the first one that I want to mention here is something that I would call a link. Okay, a link is a type of member that basically has a pin on both ends, and it doesn't have to be horizontal. It can be vertical. It can be at some other angle that has a pin on each end. Okay, so I brought an example of something that works this way. The blade on a hacksaw, right? It doesn't have to be this, but basically what you have there is you've got a pin right there and you've got a pin right there, and you can pull on this hacksaw blade. I suppose you could push on it a little bit. If it was thicker, you could push on it more, right? You could actually apply both a compressive force to it as well as the tensile force that it's actually carrying. And that's actually a good point that I should probably bring up too. Tensile versus compressive. What do we mean by those two things, you think? Okay, tensile is basically something that tends to try to elongate something, right? Whereas compressive tries to make it more compact. Like if you're pushing in on something, then that would be a compressive load or a compressive force, or later on you're going to learn about compressive stresses. Versus if you're pulling on it and trying to make it longer, then that would be a tensile force or stress, okay, trying to make something longer. So something like this is a link. If you have a situation like this where you have pins on both ends and there's no other forces acting on the body anywhere else, then the only kind of force that can be carried in this thing is either a straight elongation kind of a thing, right, a straight tensile force, or what's the other possibility? Straight compressive, right? If these are the only two forces applied to it, and there are no other forces applied to it, these are the only two ways that you can have equilibrium for a part like this. This is assuming that your pins are frictionless, meaning that you are not actually able to apply a twisting action at the pins. Okay, so if you see something like this where it's got a pin on both ends and there's nothing else connected to it, then you can assume that the force acting in that member will be along a line between the two pins, right? This will be what we call the line of action of those two forces, okay? And if you see a member like this, you know that it's got to behave that way, okay? Well, this brings up another good point. I probably should talk about a pin, right? A pin, or, you know, we think of this as maybe a rivet or a bolt, something along those lines. If you have a member that is connected with a pin, so I'll just kind of show part of a member coming down, and it's coming down into something like this. Okay, how does that pin constrain the member? So this right here is a member. Okay, what kinds of things is that member allowed to do versus not? Okay, well actually this brings up another good one, is that this symbol right here, this symbol means that this is fixed. Okay, whenever you see the hatch marks like that, it means that's not allowed to move. Okay, and so if that's fixed, then it means that we are holding this pin at a particular place, and we're not allowing it to translate left or right or up or down. Okay, so what does that mean as far as the member is concerned? Yeah, the member is allowed to rotate around the pin, but it is not allowed to translate at the pin. So I brought in an example that this happens. This is a wire stripper and cutter, right? And what you see happening there is that these two pieces, this handle right here going up into this jaw and this jaw here going down into this handle, those two pieces are not allowed to translate relative to one another at that location, right? It's being held from translation at that point, but what can they do? Right? They can rotate freely, right? So this is how a pin behaves, and this is why when you have a pin like this, that's why for the link, you end up with being, just having a force along that line of action only. All right? So that's the idea of a pin and a link. Let me show you another symbol that you might run across a little bit later. You might see something that looks like this. Okay, where I put a little triangle over on one side and a little circle over on the other side, and then maybe we'll load some things. We'll load that structure with some loads on it. All right, what do you think those symbols mean? Okay, this is, by the way, this is a beam. Okay. Let me show you that the symbols actually do a pretty good job of representing what we really mean. So let me actually kind of put this up here. What if I actually set something up like this? Okay. How am I constraining that beam? What's different about one support versus the other? One's sturdier, okay. Okay, this one over here prevents vertical movement. Actually, both of them prevent vertical movement. What does this one do that this one doesn't? Yeah, so this, well, I think I heard someone say this one won't allow it to move left and right. Okay, whereas this one over here, all by itself, it does allow it to move left and right. Okay, so if you see a symbol that looks kind of like a roller over here, that is what this is. How do we interpret that in terms of what it does to a body? Okay, I'll draw a quick free body diagram here. It means that we would only have a vertical reaction possible from a support like that roller. Okay, whereas over here, this is basically just another way of saying the same thing as a pin. It's the same kind of reaction as a pin. So what would we say in terms of how much it is constrained at that location? Yeah, so one way of saying that is that you would react a force vertically and a force horizontally, however much force you needed in those two directions to keep it from moving. Okay, so these are just some ideas, some different symbols that you may run across when you start looking at some of the homework problems that we give you. And I didn't want you to be out there on your own without some way of sort of translating what these symbols meant as you looked at them. Okay? If any other symbols pop up and you are confused by them, please let me know, and I'll try to make sure that that's not the difficulty, that you're just trying to interpret what the diagram of the given problem means, right? We don't want that to be the obstacle. All right, so that's my little discussion of supports and connections. Well, what I want to do now is go down into another example problem. Okay, so this is the example problem that I want us to solve. And not only are we going to solve this problem, I want to do this problem and do the solution in Mathcad, if possible. Okay? So, what's going on in this problem? Let's take a look at it. We have a drum that weighs 200 pounds. The drum that weighs 200 pounds rests on a sloping surface, right? The slope of the surface is 10 degrees elevated relative to horizontal. Okay? Right here. This height from the center of the drum up to where this link is connected up at the top is 25 inches, and it's 15 inches from the center of the drum down to where this spring is connected. Okay? And the spring, I'm just giving you there that the spring is carrying 90 pounds of force. What direction you think the spring might be carrying the force? I know I didn't say it, and it actually could, I suppose, carry it either direction. But if it's connected like this with no other supporting, then you could probably safely assume that it's only supporting tension, a tensile force, not a compressive force. Okay? So it's a tensile force of 90 pounds. And what we want to do is we want to find the force carried in link AB and the force carried not the force carried, but the force applied between the surface of the drum and the surface that it rides against. Those are the two pieces of information that we want. All right, we good on what we're trying to do? All right, so what should we do? Good job. That's right. We should draw a free body diagram. This is always our first step, right? So to draw a free body diagram, what's the first step of that? Say what? Draw the body. Yeah, you decide on the body that you want to analyze, and then you draw a picture of it. And so I'm going to do that. Here's my body. Okay, that's the drum. And I've shown it free of all interacting bodies. So mentally, I am saying this thing is floating in space right here. There is nothing attached to it. It is not in gravity, nothing. Okay? So that's our first step. I've identified the body, and I've sketched the body free from all interacting forces. Now what? Right, so now we go back and replace all the forces that we removed in the first step. But we do them as force vectors, and we try to label the things that we know. Okay? So what force should we identify first? Okay, spring force, that's not a bad one to maybe look at. So there's a force that comes down at some direction like this. We know the value of that one, right? 90 pounds. Okay, good. What else? Yeah.
Why would it be compressive force? Why would that be?
So there's two layers to the answer to that question. The first layer is basically this, that if you see something that's slender like that, like if this is a true representation of what that spring looks like, it is highly unlikely that you're going to be able to carry a 90-pound force on a slender member over that length. Okay, so that's the physical answer to the question. Now, could you arrange some sort of a spring system that maybe could put a compressive force there? Yeah, maybe you could, which is why at the very beginning I basically said, let's assume that's got a tension force in it. So as far as the solution to this problem, let's just take that as a given, that that's a tension force. But I do have a good reason why I say that's a tension force, because this would not be a good way to connect that spring if what we're trying to carry is a compressive force. We would need my diagram's not adequate to show what would be important to have there if we wanted a compressive force. There is nothing that would, at least in theory, prevent you from putting a compressive force in that direction, but you'd have to just come up with the right kind of structure that could do that. All right, so we've gotten one force on there. What else do we need? Okay, I think I heard someone say we should probably put something on there about the direction of that force, and I'm okay with that as an idea. How do we put down some directionality associated with a 90-pound force? Okay. Go back and use our idea of slope that we touched on last time. For a rise of 15, we have a run of 30. So now we've established the direction of the 90-pound force. Okay? What next? There's another easy one we can put on there. Weight. Okay, and I'm showing that weight applied to the center of gravity. What's the magnitude of that weight? Okay, 200 pounds. And it goes straight down, right? That's a good point to make here, is that if you're given a problem and they don't make a statement about what direction gravity is, you can assume that however it's oriented on your page, gravity's down, right? So that's another good point. So there's our 200-pound force. What else do we have? Okay, we know a 10-degree angle for something, right? That's a given in the problem. What is that used for? Okay. Well, let me ask you this. Is there another force acting on the drum? All right, we just got gravity, right? That's the 200-pound. Yeah, where it contacts the surface there is a force there where it's contacting the surface, right? So we're going to show that force right where it is applied, like right here. Okay, and its line of action, I may not have drawn it perfectly there, but its line of action extends right through the middle. How do I know that its line of action extends right through the middle of the drum? Okay, this is a good point to make here. Wherever you've got contact between two bodies and it's like rolling contact, and especially in this case because we're not applying any torques to the drum at all, okay, what that allows us to see is that there will be no tangential component of force that exists between the surface of the drum and the surface that it's riding against. It means there will not be a force kind of this direction. The only force that we're going to have is one that is normal to that surface. Okay? We could sort of prove that to ourselves if we thought about this drum and the rest of our forces are acting at B and there's no torques that are happening on B. That would mean that there can't be any sort of a lateral force that's happening on the surface. So this force has to exist along a line that passes through the center of the drum. Okay? Well, so what angle should I show as far as this force? By the way, that force, we don't know what its value is yet, right? So we should probably label it with what? Okay? Yeah, we can label it some way that's descriptive. Someone says F what? Okay, fine. F1. Sounds good. Do we know anything about the direction of F1? Okay, it's 10 degrees has something to do with it. Should I put it like this, where I've got, I may as well go ahead and establish a reference frame. Should I put it to where I've got 10 degrees up here? Or not? Okay. I hear several votes for no. Why not? Okay. What I like to do in these situations is sort of take it to its limiting cases. What if it wasn't 10 degrees? What if it was 0 degrees? Then F1 would be acting straight up, right? So what we need to see there is that whatever we pick as far as where we measure this angle, it should end up having a consistent direction relative to that if it goes to 0. And so what I would say makes that happen is if I put the 10 degrees right here. Would you agree with that? We can also take it to its other limiting case. What if it became 90 degrees? What if the 10 degrees that I have here became 90 degrees? That means this surface would become vertical, which means that the force would be horizontal. Does that still work if I measure that angle right there? Yeah, if that became 90, what direction would this force be acting? So it looks like that works. I've checked 2 points and they both work. Okay, so it looks like this is a valid way of measuring that angle for F1. All right, now what? Okay, we also need this force in member AB. So I'll draw that up like this. Maybe I'll name that FAB. And then what? Okay, rise over run. We know the 2 dimensions of this thing, so we know it has a rise of 25 for a run of 30. All right, so anything else that I need on my free body diagram? I've got my reference axes. It looks like I've got my slope for 2 of the forces and an angle for the other force. I've got labels on everything. We looking good? It looks good to me. All right, so now that I've got a good free body diagram, I'm going to take a little shot of this free body diagram and I'm going to drop it into Mathcad, which is where I'm going to solve this problem. All right, so there's my figure. What do you want to do first? We probably should put in our parameters, right? The things that actually sort of drive the problem. So maybe what first? I'm going to name one of them F spring. What's F spring? It's the spring force. I'm going to call it 90 pounds. Make this a little bit bigger for everyone to see it. Okay, so that's one of my parameters that goes into the problem. What's another parameter? Okay, yeah, that is one of the things we're trying to find. We don't know that yet, though, right? One thing we do know is the weight. So I'll name a variable weight and call it 200 pounds. What else do I know? I know that angle there, so let me name it theta 1. And I'm going to call that 10 degrees. All right, what else? Okay, maybe I'll name one of these the rise of the spring. And what is that? 15. The run of the spring will be 30. What else? Rise and run of the link, right? So maybe I'll do rise. I'll just call it rise AB. How about that? I've got nice labels on those. So I'll go ahead and call that rise AB. It's 25. And run AB is 30. Okay? And that basically takes care of, looks like, the givens in the problem. All right? Good so far? So I'm going to take all of those and highlight them. Remember, that's just what I like to do. Anytime I've established the parameters of my problem, I usually highlight them so that I remember later on those are things that I'm expecting may change for a similar but different problem later on. All right, now what? Well, I'm going to teach you a new method. Okay, we're going to do something a little different today. I'm going to teach you something that's called a solve block. All right, solve blocks are really nice. Okay, they are ways that you can solve systems of equations. You can even solve systems of nonlinear equations using solve blocks, which is a really nice thing. Okay, so the first thing you need to know for a solve block is that internally, Mathcad is doing a numerical method on doing the solution to that solve block. Here's what that means. It is a very sophisticated guess and check technique. All right? It's not just a blind guess and check, but it is a guess and check style of technique, which means it needs to have an initial guess for it to try, and then it will, try that out, see if it works, figure out how bad it is, and try something new, right? Under the hood, that's what Mathcad is doing. And so I'm trying to give you a little bit of an appreciation for why I'm going to do this next step. What we need to do as the next step is define the variables that we want to find and give them an initial number. Okay? So one of those would be what? What's one of the things we're trying to find? Okay, F1. And when we do this, we need to give it a number that is in the correct units. Okay? It doesn't need to be the correct number, but it needs to be the correct units, right? Or at least the correct unit type, right? In this case, a force. So some value of force I need to plug in there. Another tip I'll give you at this point, don't use 0, all right? Even though it won't stop you from using 0, the number 0 creates havoc on numerical techniques often. And so it's just a good idea to avoid it if you can. So we are just going to put in here 1 pound. Okay, what else are we going to be trying to find here? FAB. Okay, and I'm going to put in 1 pound for that as well. All right, now this gets into, maybe will help explain why I like to have some of my fields highlighted one way. I like to highlight fields like this in another way. I usually use blue. Why do you think I do that? Yeah, basically this is so that later on when I start looking at my sheet, I don't get confused and think, oh, I'm going to change that, and it's going to change something about my solution. And probably not, right? Those were just initial guesses that I used. So anytime I'm using initial guesses in a solve block, I will basically always highlight those blue in the sheets that I write. Again, that doesn't do anything other than just make a note to myself for later on. All right, so that's the first step, is you've identified the things you're trying to find, and you've set them equal to some initial guesses that have the correct type of dimension on them, in this case, force. Here's the next step of the solve block. You type the word given. All right. Make sure when you type the word given, you don't hit the space bar. All right, what happens if you hit the space bar? Yeah, it turns it into a text region, and now it's not going to look at that as if it's anything with respect to math. So don't hit the space bar, just type given. And when you're finished with that, you're done with that little entry. All right? And below or to the right of given, we're going to start writing our equations. Okay? What's one of our equations we can write? Okay, I'm just going to put in here a little note. This I am going to make a text region. I'm going to say this is the sum of forces in X. Just make a tiny little note right there so that you know what I'm about to do. I'm going to sum forces for this free body diagram in the X direction. Okay? So how do I do that? Okay, we just start with a force, right? Which one do you want to start with? Okay, F1. F1 points to the right or to the left? To the left. So I'm going to say this is going to be negative F1 times what? I want just the x component, and I have that 10-degree angle measured relative to the vertical. Okay. I want to pick probably the opposite component from where the angle is being measured, right? If I want horizontal, I want the opposite component. And so I'm going to pick the sine of that 10 degrees. And the 10 degrees is just, I named it theta 1. Okay? And so there I've taken care of the x component of F1. What's next? What's the next one you want to do? You want to do FAB? Okay. So I say, does it point left or right? Left, right? So I'm going to say minus FAB, right, times what? Okay, that's right. So I don't have an angle on this one. I could come up with an angle, but that would be extra steps. I'd rather just come up with what is the x component based on the slope indicator that I have on that force, right? So I put in what? Run over square root, okay, of rise, and I think I actually had, I need to change the one up there too. It's the run of AB squared plus the rise, or excuse me, rise of AB squared plus the run of AB squared. Up here I had run, but I should have named it what? Run of AB, right? Run sub AB. Okay? So that takes care of FAB. What's next? Okay. I also have that 90-pound force, right, which I named F spring. But I only want the x component. So what do? Multiply by sorry, there we go, over the square root of the rise of the spring squared plus the run of the spring squared. All right, any other forces that have x components? No? I don't think so. All right, this is the next thing that's a little bit tricky about the solve block. We're going to introduce yet another kind of equal sign. Okay? This sign that we're about to put in here is called a Boolean equal sign. All right? If you want to get to it from the menus, one of the menus is a Boolean menu, and you see it right up here on my, at least in my instance of Mathcad right here. There's a Boolean equal sign right there. This Boolean equal sign actually works similarly to the double equals that you use in your Arduino. It is a question. It is this equal to this? All right? That's what that equal sign really means. That makes sense if you think of this being a sophisticated guess and check technique, right? Each time it runs through it, it says, is this equal to this? And if it's not, it changes something and tries to make this equal to this. Okay, so that's what we're going to do to get that equal sign in general is you hit Control equals. You hold down Control and you type equals. Okay, and what do we put in there now? 0. All right, what's next? Okay, tell you what, I want to try to keep all this in here. I'm just going to move this down. It doesn't matter which order you put these in. I did a copy and paste here. I'm going to do the y direction now. What changes? Okay, yeah, I should probably put in rise here. I think that was one of the things you said. And rise here. Okay, what else should we do? Sine maybe should be cosine. While we're at it, the other thing we need to change, or we need to at least check to see if we need to change them, are the signs of each of my entries here. Okay, so the very first one for the F1. Okay, I'm doing this in the y direction now. Should that be a minus? Does F point up or down, generally speaking? F1. Up. So I probably don't want this minus sign here that was appropriate for the x direction. It's not appropriate for the y direction. All right, what about the next one, FAB? Okay, I agree that that should also be plus, right? Oops. Sometimes it takes a little bit of practice with this, trying to get the, if you're trying to edit something, trying to make it happen. Some people get frustrated and they erase the whole thing and they start from scratch. You'll get it though. What about the next one, the spring? Okay, that one stays negative, right? Because vertically, it's still pulling down. Okay? Am I complete yet, or am I missing something? Right, we're missing the 200 pounds. We didn't have that in the x because there's no component of that one in the x direction, but I do need it in the y because it's entirely in the y. So what do I do? Okay, so I take all this and say minus. I could type in 200 pounds, but a more powerful way to do it would be minus that variable that I defined up there, the parameter for the problem, so minus weight. All right. So those are my two equations. I have two unknowns in those equations. How do I solve? Well, one way of doing it, I'll show you the quick way of doing it first. The quick way of doing this is to type find. Right? You type find, then you put in the things that you would like to find. So we want to find FAB, probably, and F1. So I hit find, opened a parenthesis, typed in FAB, comma, F1, and then close the parentheses. Now I'm going to hit my evaluation operator, which is just what? Just a plain equal sign. Okay. It gives these answers in terms of what unit? Newtons. If I want to be consistent with what it was given in, I can change this to pounds. And let's spend a couple seconds looking at these results. Okay. First of all, you'll notice FAB, the result came out negative. What does that mean? Ideas? Okay. All right. I hear some, you're dancing around the center part of what we need to think about with this. Here's what it means. Up at the very beginning, we assumed directions for the force acting in the link and the force acting between the drum and the surface, right? We don't necessarily, we weren't able to know necessarily if those directions were correct. We know the direction of the line of action, right? We know that it goes along that slope, but we didn't know whether it pointed away or toward, right? That was an assumption we made at the very beginning. So then we work through the problem and we get to the end and we get a negative number. What do you think it means?
Force in the opposite direction.
It means our assumption was opposite of what it should have been, right? It really points the other direction. Okay? Is that a problem? No, it isn't. All right? it's not a problem because it is actually correct. There is a negative force applied to the drum according to the arrow that we have applied to the drum, right? So it means that even though we put the arrow up here, which means that we're saying that we're assuming that the force in the link is going to try to take the drum and pull it that way, right? What is the link really doing? The link is really pushing this way. But what we have drawn on here, the arrow pointing this way with a negative number, that implies the same thing, right? That implies that we're pushing on it, not pulling. So it's really not a problem, right? But it's still important. It's important that you draw your free body diagram. This is actually one of the reasons why your free body diagram is important, so that when you get to the end and you get results, you know how to interpret the results, right? Because if you had made an assumption the opposite direction, then you would have come up with a positive number at the end, and that would have told you the same thing. Do you agree with that? Okay, so this is another really good reason why we need free body diagrams, is so that we can properly interpret the results at the end. All right, one other thing. Yes, got a few hands up here. Yeah, so it probably shows up in newtons like right here. Is that what you're seeing? Like that? And so to change the output of one of these evaluation operators, you click on the little black box right there and you type in the units that you would like. Okay, yes ma'am.
When I type in find FAB and then comma F1, parentheses, it says that the variable is like undefined.
Okay, so there's a few things. That, unfortunately, that error message doesn't tell you a whole lot. Basically that says, I couldn't do it for some reason, right? There's a few things to check. First of all, you need to check and make sure that you actually correctly put in your initial guesses, right? The other thing to check through very carefully is make sure that you didn't do any implied multiplication, like where you thought you put in multiplication, but you don't actually have a multiplication sign. The other thing that can happen is you may end up with inconsistent units somewhere if, if one of your calculations isn't typed just right. So there's a lot of things that can happen there. Probably won't be able to troubleshoot it completely from up here, but be happy to get with you and try to look at what's going on after we're through with this. Other questions? Yes. Are you using prime? Okay, so this whole process is very different for prime. I probably should have said something about that at the very beginning. It's actually not extremely different. It's kind of similar, actually. But the big difference is in Mathcad 15 and earlier, you could just do solve blocks anywhere you wanted to on your page. You could type a given, you could type in your equations that establish the constraints of your system, and you could hit find and it would work. In Mathcad Prime, you actually have to go up to the ribbon on the top, and I don't remember the exact menu, but there is a choice that you can put in there that is put in a solve block. It's under math, okay. So you put in a solve block, and then it gives you basically the same places where you can put these kinds of things. And other than that, it really works basically the same. All right, let me show you one other thing here that I don't usually use the find command exactly like this, okay? The reason why is, let me show you the reason why. Watch what happens now if I type FAB equals. All right, and let me change that to pounds. Is that what you would have expected? Okay, good. I mean, you guys are on the right track. So, that is something that I wouldn't necessarily have expected whenever I was first starting to use Mathcad. But it makes sense if you think about what the evaluation operator is doing. Basically, what you're doing is you're asking a theoretical question. If you need to satisfy these constraints right here, what value of FAB would you need to satisfy those constraints? And the find command tells you what that value would be. but it doesn't actually assign that value into the variable, right? It leaves the variable alone. So it still has the 1 pound in it from where we defined it up earlier with the blue. So that's sometimes annoying to people, and sometimes people want to actually update their variables with the new values that you just calculated. So how do you do that? I'll show you. Okay. We have to put in here, we have to put a matrix in here. Okay, there's a couple ways you can get a matrix. Control M will do it. The other thing, if you don't want to remember that keystroke, there is a matrix toolbar, and see if I can, it's right up here in my instance right here. It says matrix. So you can click on that button, or you can hit Control M. Maybe you can. I don't know why it's not working right now. But anyway, it might have something to do with my screen recording software I've got going. I don't know. But anyway, I hit the button and I get my insert matrix, 2 rows, 1 column. All right. What do I put in here, you think? I put in the names of the variables that I would like to update. Now I hit my assignment operator. And then what? Now I type find. And I put in the variables that I would like to find. Okay? And when you do this, it makes little green squiggles. What does that mean? Remember, the green squiggle means that you updated the value that was in a variable, right? That's a good thing in this case, right? Because that's what you were trying to do. You're trying to replace the value that you originally had in FAB and in F1 with the values that you just came up with. And so then, if you want to check and see what those values are, you can now use your assignment, or your valuation operator and see what those values are. And that is how I typically will use a solve block. Yes, sir.
What happens if you call F1 or FAB before you reassign it?
If you call it before you reassign it,
Yeah.
like if you go up here and you say FAB equals like this, it hasn't been reassigned yet, right? So whereas if I put this below or to the right, it has been reassigned. Okay, so this is another, emphasizes the point again that where you put things on your page matters. Okay. Questions? Yes, ma'am.
Okay, so I got the original find to work. I looked back and I was like multiplication where there should have been. And then,
Okay.
but now when I put the matrix in,
Mm-hmm.
it says my F1 is undefined.
You have to delete the old find.
Right.
Okay.
Yeah, you can't put in another find. So yeah, the given that you put up here pairs with just one find, right? And once it does that, Mathcad says, I've processed that solve block and I'm done. Okay, so that's a good point. All right, any other questions? All right, that sounds good. That concludes our lecture for the day.